So we discussed earlier, for classification, we will use a different algorithm, but the concept is same. We need to change the hypothesis function. And we also need to change the cost function. So what is costing here? Because here we are not going to predict some real number. The difference is always right or wrong. So 0 or 1, something like that. So logistic regression, it is named that way for historical reasons and is an approach to classification problems, not regression problems. So we are not regressing to a value. We are predicting a class here. But somehow it's if people named it, we'll come to know that because they use the same concept, that's why they are putting the regression word here. So there are different types of classification problems. The famous or important one is the binary classification. Of course, if we understand binary classification, we can use even multi-classification also. By using binary classification, we can do multi-classification problem also. There we will take it, see 1 versus all. So then it's in remaining things, then again we will create 1 versus all like that. You may need to apply many times this binary classification for multi-classification problem. But anyway, when we take an example, we will understand better how do we use binary classification to solve the multi-classification problem. Here, when we compare with linear regression, our output vector y being a continuous range of values, it will only be 0 or 1. Earlier we have seen in linear regression, we had any real number can come when we apply the linear regression. Now the output we are restricting, output should be always either 0 or 1. So your y column will have only 2 values, either 0 or 1. You can see in the example right side. So you are giving explanatory variables x1, x2, x3, temperature, humidity, wind pressure. Based on that, can you predict, will it rain today? If it rains today, that is called positive, we represent with 1. If it doesn't rain today, then we represent with 0, negative. Some people also put 1 and -1, but we take the notion of positive always we will represent with 1, negative we will represent with 0. So positive means the question answer if yes, that is called positive. If the question answer is no, that is called negative. Here 1 is positive, 0 is negative. Here 1 means yes and 0 means no, where 0 is usually taken as the negative class and 1 as the positive class. But one can assign any representation to it. So we'll get into some statistical and probabilistic to understand. If there are 2 variables, like hours studying and a probability of passing exam. So if people doesn't study anything, there is 0 probability to get past the exam. If they start putting some hard work and gain some subjects, you can see that it's from left to right. If they cover only 1 chapter, then fortunately there are only 2 questions, and in the chapter 1 have 1 question, then there is some probability to get past the exam. So like that, very minimal it will go, but if you cover substantially half of the things, means 50% of the things, like there are 5 units you think, or 5 hours need to spend, but you spend 3 hours, you gain the knowledge, what you can gain in 3 hours. Then enormously the probability is, it's not a linear, it's in the same line it is going, it's steeply it is increasing after 2 and between 3. Then up to 4 it is still increasing, but after 4 it's even if you read that 1 hour extra or not, it only will increase your grade, not passing the exam. So like that, here it is not a same steep, unless it will increase according to the hours. So those people who put less than 2.5 hours, whatever that here it is coming like that, then their probability is less. So whoever puts more than 2.5 hours, their probability is minimum of to get sure that all of them should pass it, then they should spend almost 5 hours a day. So it is not linear. There are not many linear functions you can find. You can see that many nonlinear things. It is one of the nonlinear thing where the slope, or in other words, the steep will decrease and increase not uniformly. For a line, the steep is always uniform. So when we want to predict based on hours of study, this is not a linear. Let's see, we can write something, probability of getting pass is some function, it's a linear function of the hours of study, because it is not a linear function, which we have seen here. When we are plotting, we are seeing that it is not a linear function. The steep depends on different things. So what approach we'll take to solve this problem? So use linear regression and map all predictions greater than 0.5 as a 1 and all less than. Okay, we assume that it is a linear. Still, we want probability. What is the boundary of the probability? Can probability more than 1?
In between 0 to 1.
0 to 1.
0 to 1. So whatever we need to get prediction, if we consider it, if we want to predict probability of passing exam based on hours of study, we need to restrict our output should be between 0 and 1. Okay, we assume that we will get a function which will convert all real numbers between 0 and 1. Then can we do a linear regression? That is the question now. Use linear regression and map all predictions greater than 0.5 as a 1 and all less than 0.5 as a 0. So it's a simple transformation. Whenever you get more than 0.5 in a linear regression, you assume that is 1, and whenever it is less than 0.5, you assume it is 0. So what is drawback with this? Classification is not actually a linear function. So this method doesn't work well. So we have seen even the graph also, it is not linear, right? So it doesn't work. Even if you want to predict that some real number, anything more than 0.5, it is 1, anything less than 0.5 is 0. What is the middle number of the 0 and 1? 0.5, right? That's why they are taking anything, if you are getting more than 0.5 probability, they are rounding off to the 1. Less than 0.5 will round it to be 0. So here we change the hypothesis. Earlier we were having hypothesis any real number. Now we are restricting 0 less than or equal to h theta x less than or equal to 1. Whatever you compute the function from the explanatory variables, the value should be between 0 and 1. So need to predict values either 0 or 1, hence hypothesis should satisfy this. Okay, so then what we do is, usually this theta transpose x. What is theta transpose x? Anybody remember in linear regression? Y predicted for a particular value, y predicted is equal to what? There, theta transpose x, right? Theta 1 x1 plus theta naught x0 plus theta 1 x1. This you should see as this is a row vector theta transpose, because theta was a column vector earlier. So theta transpose will become row vector, theta naught, theta 1 dash 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 theta n. X will become a column vector, x naught, x1 dash 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 xn. Then you multiply, you'll get theta naught x0 plus theta 1 x1 plus theta n xn. So that is nothing but exactly your hypothesis in linear regression for y prediction. So you are using, if you want to use linear regression, you use linear regression first on basis of your explanatory variables and fix some thetas by using linear regression. But you want the number is to be between 0 and 1, you bring this whole thing, theta transpose x, so that it is between 0 and 1. So that is what G function. So we need to find out another function, which is called transformation of the linear regressive value to in restricted limits. So if we write Z, Z means our y predicted, but it is not y predicted here, because we are just getting some Z value based on theta transpose x. When you apply G function, that should be transformed into between 0 and 1, because we want to transform that into the probability. So gz equal to 1 plus 1 by 1 plus e power minus z. So what is the maximum value for this? 1 by 1 plus e power minus z?
1.
If you take z is the real value, right? Because theta transpose x is a real value. Theta naught x naught plus theta 1 x1, all those things. So z is a number, real number. Now see, what is the maximum minimum for this? When will you get minimum for this function? Denominator should be
Maximum.
Right.
maximum. So when will be the denominator maximum? 1 is the constant, that won't make maximum or minimum, right? Only e power minus z should make
When z is
or
maximum.
minimum. Okay, e power minus z is minimum
When z is maximum.
when z is maximum. Means z equal to infinity. So when z equal to infinity, what it becomes? E power minus z? 0.
Almost tends to 0.
0. So 1 by, this total value will become what? 1 by 1 plus
0. 1.
0. So 1 you are getting, right? The maximum value for the gz will be 1. When will you get minimum for e power minus z? When you get this whole thing is minimum. When denominator is very high, right?
Yes, sir.
When a denominator high means e
Z
power
is
minus z
minimum.
also should be high. So when will you get e power minus z high?
Z
When z
value
is minimum. When z
Z
tends
value
to
is
negative infinity.
minus infinity. Tends to minus infinity. Minus minus will become plus. So e power infinity is infinity. 1 plus infinity is infinity. 1 by 1 plus infinity is infinity. So 1 by infinity will become 0. So whenever z takes the negative large values, then it becomes 0. And whenever it takes positive z values, it becomes 1, right? So always gz value will be between 0 and 1. This g is called the sigmoid function or logistic function. So that's why this name called logistic regression. So gz is called a sigmoid function, which is also called the logistic function. So here some examples are given. Z equal to 0, e power 0 equal to 1. So when z is becoming 0, you are getting exactly off. When you are getting minus infinity, then your gz will become 1. When you have positive infinity for z, your value, positive infinity it is 1. For negative infinity, it becomes 0. So gz greater than or equal to 0.5 when z greater than or equal to 0. Otherwise, gz less than 0.5. So that is what this says. So here you see it's the graph also an interesting thing. The steep will become very high after 2.5 and minus 2.5. Minus 2.5 till minus 2.5 there is no steep, and after 2.5 there is no steep. Means it's when you are moving towards here 0.5 in the case gz greater than 0.5 and z greater than or equal to 0. So more than z equal to 0. Whenever it is more than z, then it almost becomes to 1. Means very steep. Afterwards, it becomes slow steep. And similarly, before 1. So the steep will become very high as you go to the ends of 0 or 1. When you are in the middle, then the steep will become less. Or else it's in the beginning, the steep is very less. As you progress, the steep becomes very high. So you don't need actually to come almost 1 probability to the infinity. So even at here, you can say at 2.5 itself, almost you are getting almost 1 probability here. So the function gz shown here maps any real number to the 0-1 interval, making it useful for transforming an arbitrary valued function into a function better suited for classification. So we are now trying to predict 0 or 1 based on the probability prediction, the probability should be between 0 and 1. Then we got this logistic regression. So originally we apply linear regression function, but we won't consider that as the final value. We will apply this G for that. So if G becomes more than 0.5, then we will predict 1. If it is less than 0.5, we'll predict 1. We'll predict 0. H theta x will give the probability that the output is 1. This H theta x is not theta transpose x. This H theta x equal to G of 3 theta transpose x. So this will give the probability that the output is 1. So for example, H theta x equal to 0.7 gives the probability of 70% that the output is 1. So H theta x equal to probability of y equal to 1 when given explanatory variables and theta are your weights. So we are writing H theta x, probability of y equal to 1, provided the values of the explanatory variables and weights. Similarly, H theta x equal to 1 minus probability of y equal to 0. Probability is complementary, right? If there are only two classes, the probability of 1 is nothing but 1 minus probability of 0. That is what they are writing here. So both when you add, it should become 1. So if the input to G is theta transpose x, then that means H theta x equal to G of theta transpose x that greater than or equal to 0.5 when theta transpose x greater than or equal to 0. We have seen earlier this year, this we mentioned here, right? Gz greater than or equal to 0.5 when z greater than or equal to 0. This z is nothing but after first you get theta transpose x, that is transformed with 1 by 1 plus e power minus z. Then you see where you are getting more than 0.5 when z equal to 0. Less than 0, less than 0.5, greater than 0, more than 0.5. So that is what we are getting here. So H theta x equal to G theta transpose x greater than or equal to 0.5 when theta transpose x greater than or equal to 0. Otherwise, H theta x will become less than 0.5. Hence, same thing we are writing, theta transpose x greater than or equal to 0, we want. G is just transforming those values, right? So we are not interested in G. So we are interested to get theta transpose x greater than or equal to 0 when y equal to 1. And theta transpose x less than 0 when y equal to 0. This is what we want. So this is nothing but your linear regression equation because theta transpose is your theta naught x naught plus theta 1 x1. So we should get the weight so that whenever y equal to 1, our linear regression function theta transpose x should give value greater than 0. Whenever y equal to 0, it should give less than 0. So usually this theta transpose x, if you get a line equation, so if it is separable means if you can separate all the points, positives and negatives with one line, that is called separable. Here it is a nice classification we have. We can use this by a line, separate these two types of points in the space, positives and negatives. Of course, there are some exceptions, 1 or 2 blues are down this, means they are anomalies. But largely, it's we are able to separate them. So if we can separate with a line, then linear regression will work. If we cannot separate with the line, then logistic regression, linear regression, these methods will not work here. So if it is a multi-dimensional space, then we should be able to separate with a space, 2-dimensional space, plane or 3-dimensional plane like that. Here another example, above the plane and below the plane. Above the line, below the line like that. If they are linearly separable, then it is very good for us to apply logistic regression and get a good result. If they are not linearly separable, then we will have problems, we will not get accurate results. Even in the linear regression is also same. We are assuming the relationship is linear, that's why we are trying to put a linear regression function. If the data is not linear, then our results won't be that good. The decision boundary is the line that separates the area where y equal to 0. Here, theta transpose x. So where y equal to 0 and where y equal to 1. It is created by our hypothesis function. So if we get h theta x equal to 0 line, then whenever it is greater than 0, it should become 1. Whenever it is less than 0, the class should become 0. So that's why this is called h theta x is a now boundary of division of positives and negatives. You shouldn't see as a line. We are not regressing any value now. We are just dividing them. So we will see whether our h theta x greater than 0 or less than 0. So that's why this line or this plane are becoming boundary functions for logistic regression. So we'll see some example now. So theta equal to 5 minus 1, 0. Suppose we got these weights after fitting the linear regression. And x naught is always 1. So we will write x as a column vector 1, x1, x2. Then what is theta transpose x here? 5 minus x1 plus 0 x2, right? Theta naught x naught, theta 1 x1, theta 1 x2. So 5 minus x1 you got. So when will it become 0? Theta transpose x greater than or equal to 0 means this 5 minus x1 should become greater than 0. 5 minus x1 greater than or equal to 0. That means x1 less than or equal to 5. So whenever x1 is less than or equal to 5, then we will get theta transpose x greater than or equal to 0. For that, we will predict as a class 1 because it is greater than 0. In this case, the decision boundary is a straight vertical line. This x1 less than or equal to 5 will take x1 equal to 5. x1 equal to 5 means in a two-dimensional space, x1 and x2, it is a line parallel to y, means vertical line on x. So in this case, so this is the x equal to 5 line. So x won't change, only y values will change, right? So this is a line which we are getting now by using this theta transpose x greater than or equal to 0. And everything to the left of that denotes y equal to 1, while everything to the right denotes y equal to 0. So here red equal to yes, blue equal to no. Of course, there are no blue points, but even then we got like this. Some blue points. If blue points are there, they should fall to the right. If red points are there, they should fall to the left because they are yes and blues are no. x1 less than or equal to 5, we got to say theta transpose x greater than or equal to 0. We want greater than or equal to 0. So x1 less than or equal to 5 means that is left side of this line. All those points will have x value less than 5. Right side of this line, all those points will have x greater than 5. But we want it to be positive, x1 less than or equal to 5. So that's why all left points will classify with 1. Right points will classify with 0. The input to the sigmoid function gz, example, theta transpose x doesn't need to be linear. So you don't need theta transpose x is linear. So we want only this function is linear, right? Which is dividing this space. Could be a function that describes a circle, z equal to theta naught plus theta 1 x1 square plus theta naught x2 square also, or any shape to fit our data. So we are not assuming theta transpose x should be linear. Now, we cannot use the same cost function that we use for linear regression because the logistic function will cause the output to be wavy, causing many local optima. In other words, it will not be a convex function. So logistic regression is not a convex function. So we will get many minimas and maximas. So we cannot use the same cost function here. The cost function for logistic regression looks like this cost function j theta equal to 1 by m, I is equal to 1 to m, cost of h theta xi yi. So whenever you are predicting yi for given xi, what is the cost you are getting? So then sum of all those costs for each point, then you'll get the cost function for the entire data. So you need to reduce that. So this is in general setup they are talking. J theta should be minimal. The minimal of cost is nothing but you should get minimal deviation at each point, what we are trying to predict. So cost of h theta xy equal to minus log of h theta x if y equal to 1. Cost of h theta xy equal to minus log of 1 minus h theta x if y equal to 0. So we need to get a different cost function now. So what is this? We'll see now. If y equal to 1, then your h theta x you take. Then what is when log h theta x will become high value? What is the value if h theta x equal to 1? Minus log of h theta x. First get the log of h theta x. What is log of 1?
0.
0, sir.
So log of 1 equal to 0. So when h theta x will become very high values, what will happen? Log value also will become infinite, right?
Right.
Yes, sir.
So minus log h theta x is what?
If h
When will it
theta
become 0?
becomes maximum, then it will
Minus
become
infinity, right? If h theta x is infinity, minus log h theta x infinity, this will go to minus infinity. If h theta x is infinity.
Yes.
Okay. So when will it become 0? Log of a power
When
b
h
is
theta
how
x
much? Yeah, you're right. H theta x should be
1.
log of a power b is b log a.
Yes, sir.
So you can write minus 1. So h theta x power minus 1. 1 by h theta power x you can write. So 1 by h theta x will become 0 provided h theta x will become infinity. So whenever you get h theta x infinity, you will get 1. So that is what they're writing here. So if y equal to 0, what will happen? Your h theta x. So when do they cross? The more our hypothesis is off from y. So you need to get y equal to 1, but your hypothesis function is not greater than 0. So what will happen? Then you will get more cost. That is what the idea here. So if your class y equal to 1, your cost is saying, if your h theta x is towards 1, you are getting less cost. You see that this y axis has the cost value. So cost value is when you are getting more in the first graph. The assumption is y
H
equal
theta
to
x
1.
is towards
0. If your value is close to 0, then you are incurring high costs because you need to predict 1, right? So h theta x greater than or equal to 0.5, that is what we want. Or h theta x greater than, yes, 0.5, right? What is your assumption? H theta x. H theta x, that is what exactly we said, right? Theta transpose x should be greater than 0. Then h is again z function, that is 1 by 1 plus e power minus z. So that should be greater than 0.5. So if it is greater than 0.5, your cost is becoming what? See this, if y equal to 1 means it is already, we know the class is 1. Then we computed from our fitting h theta x. If h theta x is greater than 0.5, somewhere here, right? So you see here, somewhere here 0.5 will come, right? So before 0.5, the cost is becoming infinity. Means you need to predict 1, but when you are predicting close to 0, your cost will be very, very high. When you are predicting close to 1, means greater than 0.5, your cost will become less. It is not linear, remember. Even if you move little bit less, the cost will increase multi-folds, not in linear fold. So when you are coming close, your cost is also decreasing, not it's a very drastically decreasing less. Means whenever you are making a big mistake, instead of predicting 1, you are predicting close to 0, then you are making very huge cost. Similarly, y equal to 0 you take here. Y equal to 0 means your h theta x should be close to 0, right? Then you are predicting right. But if you are predicting close to 1, your cost will become infinity. Means you are making a big mistake. So that is what we are putting in this hypothesis function. So that whenever you are coming close, when y equal to 0, then you don't make much cost. But when you are moving towards 1, when it is to be predicted 0, then you make huge cost. So that is what this is taking care of, minus log. That's why this minus log means it penalizes very high when your probability is becoming in opposite direction than expected thing. If it is in the same direction after 0.5, then your cost will become less. So that is what taken care by this minus of log that. Okay. Is it clear now how the cost function is defined here? This cost function is taking care that whenever we are making mistake, huge mistake, then huge cost, less mistake, then less cost. So if it is to be positive, if or 0.6, 0.7, if you say it is 0, then it is less cost. But when you make 1 as 0, then your cost is increasing like anything, almost infinity cost you are incurring. When you don't predict 1, but it is less than 0, then cost won't become infinity. Somewhere it will be something like it. So you can see here. So that is the advantage of this taking minus log function. It penalizes whenever you are moving in opposite direction very high. When you are moving in the same direction, less cost. The more our hypothesis is off from y, y means here in this case of y equal to 1, in this case y equal to 0. For both assumptions are different. Off from y. So y should be 1, but your prediction is h theta x equal to y here. Your prediction is close to 1, no cost. Your prediction is 0, then it is very high cost. That is what it is mentioned here. The more our hypothesis is off from y, the larger the cost function output. If our hypothesis is equal to y, then our cost is 0. So if you want h theta x equal to 1 and you got 1, then your cost is 0 here. Here also, if you want y equal to 0, you got h theta x equal to 0, then your cost is 0. So cost of h theta x y equal to 0 if h theta x equal to y. Y means the classification value 0 or 1. Cost of h theta x y equal to infinity, y equal to 0, and h theta x tends to 1. And cost of h theta x y tends to infinity, y equal to 1, and h theta x tends to 0. So we are not going to derive all these things, but you should remember that logistic function is designed so that whenever you are making a mistake, huge mistake means if you need to predict probability 100% for 1, you are not predicting 100, but you are predicting 0 probability for that 1, then your cost will become very high. So the cost steep is very high when you make a big mistake. When you make small mistake, your cost also will become less. So that is how this logistic regression function is designed. Note that writing the cost function in this way guarantees that j theta is convex for logistic. So to make only one minima for the entire thing so that we will not fall into the local minima. So we want to convert the whole function into convex by taking this j theta in this form. It converts into logistic function as a convex function. So we will write only one equation for h theta x equal to 1 and h theta x equal to 0 also here, putting here. Cost of h theta x y equal to minus y log h theta x minus of 1 minus y log of 1 minus h theta x. So write them, note, when y is equal to 1, then the second term 1 minus y. If y equal to 1, then second term is becoming what now? 0 it becomes. Only first term will give you the cost. So when y is equal to 1, then the second term 1 minus y log 1 minus h theta x will be 0 and will not affect the result. When y equal to 0, what terms remains here?
Only the second minus.
Only second
1
term
is
will remain, right? The first term y equal to 0 will cancel that 0. So if y is equal to 0, then the first term 1 y minus y log of h theta x will be 0 and will not affect the result. The entire cost function is written as follows: minus 1 by m, because for each point we need to sum now, I is equal to 1 to m, minus yi, this is the given value for y in the data set, in the training data set, log of h theta xi. This is the cost for this, minus log of h theta xi, minus 1 minus yi, log of 1 minus h theta xi. So the first terms will take care of for positive values, because for positive values this 1 minus yi will become 0. This term doesn't exist. Whenever your yi's are 0, the first term will cancel, only second term will remain. So we are able to write this whole function as one equation now. So h equal to g of x theta. In the original setup, vector matrix multiplication they are writing, right? Individually, when we predict y, then we write theta transpose x, but we want to predict all y's together, then we wrote x theta. X is the matrix of x values, x1, x2, x3, we give columns like that. Then this theta is the column of theta weights, theta naught, theta 1, theta n. Then x theta simultaneously will give you exactly how many variables are there, that many. How many your instances are there, y values, that many y values will get. Each y value should be equal to one of the y value. After computing, you will get a column vector here. So h equal to gx theta, and j theta equal, this x theta will give you that column value. Then g of x theta you apply. For each value in that column, you apply g of x theta. And j theta equal to 1 by m minus y transpose log of h. We are converting this into a matrix form. 1 by m minus y transpose log of h minus 1 minus y transpose log of 1 minus h theta xi. Because your h will give you a matrix. So at a time you will get all values here, j theta. So how do we apply now gradient descent? We got the cost function. Now our aim is to reduce the cost. So we know what variables are there in the cost function. We need to take partial derivatives and get the gradient descent for that cost to be reduced. The general form of gradient descent is, as we did in linear regression, theta j equal to theta j minus alpha of delta by delta theta j of theta. This is the same equation we will take now, but your j theta has changed. As I told you earlier also, we will change the cost function. Remaining setup is same. So the cost function we designed so that because it has become probability, if it makes in a reverse direction the prediction, then it costs fews. If it is in the same direction, it costs less. So that modification we did for cost function. And we also did the real value to be between 0 and 1. We took another logistic or sigmoid function 1 by 1 plus e power minus j. Those two things we did extra here. But once we know the cost function, then it is the same setup what we did in linear regression. So theta j minus alpha of delta by delta theta j of j theta, but j theta is changing here. So j theta still we write initially h theta of xi minus yi, but h theta x will change now. So this algorithm is identical to the one we used in linear regression. We still must simultaneously update all values in the theta. So again, you cannot get first theta naught, then theta 1 like that. One iteration means all things should be updated simultaneously. So a vectorized implementation of this is theta equal to theta minus alpha 1 by m x transpose, because your h theta x equal to g of x theta minus y. This is your vectorized thing. And gradient also you can write in vectorized thing 1 by m x transpose g of x theta minus y. So how do we do? See, this completes the discussion of the logistic regression. If you have any doubts, please ask now. See, we got finally the same setup as we did in linear regression only. But our hypothesis function has been changed because it is not a continuous value. We need to get 0 and 1. So we don't get 0 and 1. That's why we are getting a probability to become 0 and to become 1. So probability should be between 0 and 1. That's why we introduced a logistic function based on linear regression hypothesis. Theta transpose x, we applied for that logistic function 1 by 1 plus e power minus theta transpose x. Of course, for the brevity, they are writing z instead of theta transpose x. That's all it's. So once you get that linear regressive value, we are converting that to between 0 and 1. And it is not a linear function, and it is also not a convex function. If we don't have convex function, this gradient descent may not give you the minimum always. It may give the local minimum. Means if there are many bumps in the curve, if it falls into one bump, then it stands there only. It won't go to the lowest bump. So that is the problem with local minimum. So we want to convert this as a convex function. To convert this as a convex function, the cost function, we introduce it that it's whenever it makes a huge mistake, then use cost, small mistake, small cost, by introducing this log function minus log of x theta x. So finally, we got this cost function. Once we got the cost function, the gradient descent is even whatever algorithms we study in future, the cost function only will change in the gradient equations. Theta j minus alpha delta by delta theta j, that up to that it is same. So which cost function you get, for that cost function you need to get the minima. So here the cost function changed, the changed cost function we are applying, and finally we are showing the same thing into the matrix multiplication, matrix values, or matrix format of the gradient descent for the logistic regression. So this is the small story of the logistic regression, how we are coming from linear regression to logistic regression. So then how do, if there are only two classes, we can represent them with 0 and 1. If there are multi classes, then what we do? So then we call 1 versus all. Expand the definition so that y can have more than two categories, y equal to 0 to 1 to n. Divide the problem into n plus 1 because the index starts at 0. Binary classification problems in each one. We predict the probability that y is a member of one of the classes of y. So you need to do n plus 1 things, n plus 1 classification problems you should consider, whether it is 0 or non-zero, whether it is 1 or non-1, whether it is n or non-1. So there are n plus 1 values, so n plus 1 fittings you need to do. For which one you get the highest probability to become 0, to become 1, to become 1, that class will be assigned for that. So here y equal to 0 to n, the first logistic regression we will build, whether it is 0 or not. Then you'll get some probability that may be close to 0.5 or whatever that it's between 0 and 1. Similarly, for h theta 1x, you will get some probability. H theta nx also will get some probability. Whichever is the highest probability, that class you assign. Is it clear, this multi-class classification? Is it understood now or not? What we are doing in multi-class classification?
But won't the cost function change if the values of y are not 0 and 1?
No, because we are considering this whole thing into two groups, right? 0 we will write as a 1, and remaining things we'll put 0 only there.
Oh.
Then you are getting the probability of whether y equal to 0 or not, that's all.
Okay. Yeah.
Positive will becoming 0 class. Don't confuse with your 0 and 1, right? First you define what is positive class, what is negative class in the new setup. Becoming 0 is a positive class for you. Becoming any other thing other than 0 will become a negative class.
Okay.
So then in your new setup, all zeros you will represent as 1, non-zeros you will represent as 0.
0.
Then you are classifying whether it is 0 or not, right?
Yeah.
your logistic regression will give you a probability to be 0 or non to be 0.
Yes.
Similarly, you go to the next one. You represent all ones as ones, remaining things as zeros here, because 1 is the positive class for you.
Yes.
Then again, you get the logistic function and predict to be 1 or non to be 1 as a probability. Like that, n plus 1 times you do, because n plus 1 classes are there. That's why it is called 1 versus all. For which class you get the highest probability in your prediction, that class you are assigning here. Prediction equal to maximum of phi h theta I x. H theta x is the probability, right? PI.
Right.
So basically choose one class and then lump all others into a single second class. Do this repeatedly, applying binary logistic regression to each case, and then use the hypothesis that return the highest value as prediction. So there are some problems which we find when we fit linear regression, logistic regression, whatever that. The first problem is overfitting, the problem of overfitting. So what is overfitting? Overfitting means it's the hypothesis function, whatever fitting we did, linear regression, that works well on the training data set. But when it doesn't work well, which was not used for the training that we call test data set, then it is called overfitting. Means it works well, we got very nice function to predict on a training data set, but when we are applying that to predict new instances, it is not predicting well. So how do we know new instances? Usually we will not have new instances, we need to wait to get the new instances. So that is not the process we use. We use the given data set itself, we divide into training data set and test data set. So test data set is not used for training. Now we will apply to predict the instances on test data set. If we are not getting good result as we are getting on training data set, then we say the fitting is overfitted, means it nicely fitted to the training, but when it goes to the non-trained data set, it is making many mistakes. That is called overfitting, means you are unable to generalize the fitting, means which will work for all the instances. Only if it is working fine for the training data set, that is called overfitting. So how to address that overfitting? Means if it is a nice function, it should get the generalization, means it should get the function so that it works well. Whatever the instance comes, it should be able to predict whether it is used for training or non-used for training. It should predict accurately. So regularization is designed to address the problem of overfitting. So for those situations, we use regularization one concept to address the overfitting. High bias or underfitting is when the form of the hypothesis function H maps poorly to the trend of the data. So high bias or underfitting means it doesn't even fit for the training data set also good. Overfitting means for training it is good, for test data set it is not good. It is usually caused by a function that is too simple or uses too few features. Example, if we take h theta x equal to theta naught plus theta 1 x1 plus theta 2 x2, then we are making an initial assumption that a linear model will fit the training data well and will be able to generalize, but that may not be the case. So this overfitting has happened because we assumed it is linear and it is very simple function. It looks, because we are adjusting this theta naught, theta 1, theta 2 based on the training data set. So for the training data set, it works well because we computed our cost, all those things on training data set. We adjusted this theta naught, theta, but it is unable to generalize for the other data sets which are not used for training. So that is one problem. So one assumption is we use a very simple function to predict, and that is doing good on training data set. So some complexity function might be there, so that we are missing. That's why we need to include some complexity in this simple hypothesis function. At the other extreme, overfitting or high variance is caused by a hypothesis function that fits the available data but does not generalize well to predict new data. This is overfitting, which we discussed. It is usually caused by a complicated function that creates a lot of unnecessary curves and angles unrelated to the data. So when you fit by taking nonlinear functions like squares, polynomial, all those things, you can fit very well the data for the data. You can fit the very well regression or weights to the given training data set. But it gives lots of curves so that it loses the generalization. So that is the problem when you take a nonlinear hypothesis. So it is usually caused by a complicated function that creates a lot of unnecessary curves and angles unrelated to the data. This terminology applied to both linear and logistic regression. So how do we address these two problems? So I again repeat, what is overfitting? Can anybody say? What is underfitting and overfitting? These two terms are important. Underfitting is also called high bias. So what is underfitting first? High bias?
It fails for both training and test data.
Yeah, when it is failing for training data set, even we don't look for the test, right? We know that it is not working on the known data set also.
Yes.
So it is, you're not getting good assumption on the training data set itself. You are making so many mistakes by fitting the linear regression. It is high bias, or it is called underfitting. What is the reason for that? Your hypothesis function is so simple. It is not linear, but you assumed a simple linear function to predict that. Okay, what is overfitting now?
So where the training data set is success, but then the testing data set fails.
What is the reason for this? You took a complex function.
Yes, sir. The function only works for what we are training, but then it should be more.
So you took a complex function so that it fits well.
Yes, sir.
There is a mathematical thing. I'm not getting into that. It's whatever data you gives, if you take enough degree polynomial, you can draw a line means curve, which passes through all those points. Then you'll get what lots of curves you'll get for that. So it loses the generalization. It is only trying to fix the existing points, but it is not looking the trend, or it is not getting the trend, how the trend happens between X variables and Y variables. That is the problem which will happen with the overfitting. Means if you take the complex function, linear hypothesis, it fits well for the training data set, but it doesn't fit well for the test data set, because it hasn't grasped the generalization. It grasped only how those points can be joined with the different polynomial degree hypothesis functions. So to reduce the number of features, one of the solution to address the overfitting is reduce the number of features. So manually select which features to keep. That is one method. Use a model selection algorithm. Okay, you select some model to reduce the number of features, or select an algorithm to select only few features out of the given all features. Second thing is the regularization. Another solution is keep all the features but reduce the parameters theta. So your theta knots, whatever theta naught, theta 1, theta 2, whatever weights you are assigning, those weights should become small numbers instead of big numbers. That is one way you can reduce the overfitting. That is called the regularization. How to keep your coefficients or X coefficients, weights, small numbers. Regularization works well when we have a lot of slightly useful features. The first solution is what? Manually select which features to keep, or use a model selection algorithm. Means which features to keep, which features to remove. So regularization works well when we have a lot of slightly useful features. What does it mean? Which method we need to apply, one or two first? If you know straight away these features are not important to predict Y, you remove them. That is the best one. But if you know that all these features will contribute something, but they may not be very effective in predicting, but they have some contribution to predict. Then you need to use regularization. Regularization works well when we have a lot of slightly useful features. If we have overfitting from our hypothesis function, we can reduce the weight that some of the terms in our function carry by increasing their cost. So this regularization they are further explaining. If we have overfitting from our hypothesis function, we can reduce the weight that some of the terms in our function carry by increasing their cost. Say, if one value is high, you take this h theta x equal to theta naught plus theta 1 x theta 2 x square plus theta 3 x cube theta 4 x 4. So suppose this. If some theta is very high, then what will remaining thetas are very small. What will happen? This h theta x, only that term will dominate it. See, suppose theta 2 is 1000, x is 1. Compute x equal to 1. If you take all ones and 1 theta 2 is 1000, what value you will get? Theta naught 1 plus theta 1 1 1 2 plus theta 2 is also 1 you take. Then 3 plus this is 1000 because theta 3 I am putting very high weight. Then 1000 plus theta 4 is also 1. So you get 1004, 1005. So what happened? This whole h theta x is dependent only on this high value of theta 3, right? Remaining 1005, 1000 doesn't make much difference even in cost wise also. So if one weight is very high, then that is dominating this whole function. It is actually reducing the contribution of x and x square, x cube, x power 4. So we don't want that situation if we know that they're all contributing things. That's why we need to keep all these weights lesser so that in generalization, what will happen? Each variable here they are taking the same polynomial x square x cube, but even if x1, x2, x3, so all will have some contribution when we are going to predict new values. So if we have thetas high, only those x variables which have this high weights, those only will contribute much. Remaining things will become insignificant. We don't want that situation if all are to be important in prediction. So if we have overfitting from our hypothesis function, we can reduce the weight that some of the terms in our function carry by increasing their cost. So to reduce this theta naught, theta 1, theta 2, theta 3, theta 4, what we do is we will add to our cost function some more cost. If your thetas are very high, then that is also adding some more cost for the hypothesis function. That is what we do, so that to reduce the cost, it will also force us to reduce the values of theta naught to theta n. So if we have overfitting from our hypothesis function, we can reduce the weight that some of the terms in our function carry by increasing their cost. We'll see that how we do that. Say we wanted to make the function h theta x more quadratic, we will want to eliminate the influence of theta cube x cube. More quadratic means you don't want higher order terms, but you don't want to eliminate completely higher order terms, but their influence should be less. Then we should put that, see, how do you make the theta 3 x cube and theta 4 x 4 values less contributory for the h theta x? You cannot change x values, right? What can you change here? Only theta values you can change because you are finding the theta values. X is the observed value that you cannot change. So contribution of x cube and x power 4 terms to be less means you need to get theta 3, theta 4 small values. They still contribute, but they are very small values. Then it becomes more quadratic, means maximum contribution is coming from x and x square terms only. So we will want to eliminate the influence of theta cube x cube and theta 4 x power 4 without getting rid of these features or changing the form of our hypothesis. We can instead modify the cost function. Earlier cost function was only up to h theta xi minus yi whole square. Now we are adding plus n1 theta 3 square plus n2 theta 4 square, because n1 points are there. N1, okay, some component of the theta cube square and some component of the theta 4 square. So if theta 3 is becoming high, then your cost also will become more. That's why minimum of theta means this also forces you to get those thetas which will theta 3 and theta 4 also should be less. Two extra terms are added at the end to inflate the cost of theta 3 and theta 4. So now for the cost function to get close to 0, we will have to reduce the values of theta 3 and theta 4 to near 0. We are not doing anything. Let's say your gradient descent only will take care, because that is to find for which thetas this whole function value will get less. That's all it's saying. So we are not getting any change in our gradient descent and method of getting theta values. So we are only increasing the cost whenever theta 3, theta 4 are big numbers. So that will force our gradient to find theta so that all theta values are small. At least for theta 3, theta 4 value small, because they are increasing cost as you increase. See, square means it's you are making squares means even small increase in the theta 3, very high increase you can see it. See, theta 3 may change only 10, but theta 3 square will change to 100. Means your cost is increased 10 times more than the actual increase in theta 3. So square, if you want to reduce still theta 3, theta 4, you can increase the theta 3 cube, theta 4 cube like that, theta 4, theta 3 power 4. So if you increase, your theta values will become still less, because your gradient descent has to find this whole value should be minimum. Now for the cost function to get close to 0, we will have to reduce the values of theta 3 and theta 4 to near 0. This will in turn greatly reduce the values of theta 3x cube and theta 4x4 in h theta x. So we could also regularize all of our theta parameters in a single summation. So all theta should be small means you can write simply the earlier cost function, you add sum of all the cost whole squares. Then you will get your cost is increased whenever theta is increased. That's why it forces gradient descent to find theta so that all theta values are small, still it fits well. So the lambda or lambda here, they used this lambda. Lambda or lambda is the regularization parameter. So like your learning parameter alpha, we are using here lambda. So again, it's this lambda. If you increase lambda, then theta should be still small. If you decrease the lambda, okay, thetas can be a little bit more. So again, it depends on how small values you want. If you want more small values, you increase lambda. If you increase the lambda, this whole cost will increase, right? If you decrease lambda, whole cost will decrease. So when you decrease the lambda, it will allow thetas to take some moderate values. If you increase the lambda value, then it takes high value. It will force gradient descent to find small theta values. If lambda equal to 0, what will this equation will become? If lambda equal to 0, what this cost function will become?
Same linear.
Same as for linear regression.
Same linear
Yeah. Regression, right? So if it is close to 0 lambda, what is happening? You are not doing anything regularization. You understand? Because
Yes,
if it is close to 0, this will become like earlier cost function only, right? So if you
Yes.
take a bigger value, more regularization will happen. So this lambda is determining how much of regularization should happen. Regularization is nothing but keep all theta values small. That is the concept, regularization. Because if some thetas are high, some thetas are less, it may fit for the data, whatever we have taken good. But it is overfitting, because some thetas are dominating when you are trying to predict new values. Only those features are contributing, remaining features are not contributing. But we don't want that situation, because we want all features to contribute. We know that they are contributory features. That's why we want to keep all thetas in uniform, small values. So that forces gradient descent to find theta should be small, but provided this lambda value. If lambda is close to 0, then you are not doing any regularization. If lambda is very high, then you are doing high regularization. Then what will happen if lambda equal to very high value? The first term, whatever 1 by 2m is there, that will become inconsequential, because this second term will have very high value. Then you are not fitting anything. You are just trying to get some small theta values. That's all. It won't fit anything. Then you will get all zeros. That's all. If lambda is very high, it forces theta should be very small, means no feature will contribute anything. Like that situation you will get. That's why you should have a balance in selecting lambda based on your results. How do you modify this lambda? Then you will plot them, lambda values, then you will see that it's in whether your algorithm is working fine as or improving as lambda increases, then you will increase. Whenever you find as lambda increases, your algorithm is not doing good, then you will stop there. So again, you need to try out for different lambda values. And you also need to get a visualization to get idea that, okay, up to this lambda changes, it is improving. After this, it is not improving. It determines how much the costs of theta parameters are inflated. Lambda will determine that. Using the above cost function with the extra summation, we can smooth the output of the hypothesis function to reduce overfitting. If lambda is chosen to be too large, it may smooth out the function too much and cause underfitting. So as I told you, lambda, then it will, your whole hypothesis is driven out, right? Only the second term dominates if lambda is too large. So you will get again underfitting. So we can apply regularization to both linear regression and logistic regression because thetas are same, right, in both equations. Modify our gradient descent function to separate out theta naught from the rest of the parameters because we do not want to penalize theta naught. Theta naught is the constant term, so don't include theta naught in the regularization terms. So if you use regularization, how your gradient descent equation, your cost function is changed now, new cost function will come here. So new cost function is earlier what we have taken, plus lambda by m theta j will come here. So it is the same setup as you got, but your cost function is changed now. Your cost function is this. So for this you will get. Now this will become lambda, your theta j minus alpha 1 by m, cost from the fitting and the cost from the regularization, lambda by m theta j. So for j is equal to 1 to n, same simultaneously you need to update them. The term lambda by m theta j forms our regularization here. With some manipulation or update rule can also be represented as theta j equal to 1 minus alpha lambda by m minus alpha 1 by. This some mathematical computation you do, then you can convert this theta j to this. This alpha is your learning parameter. So you can expand and see, then you will get this final equation. The first term in the above equation is 1 minus alpha lambda by m will always be less than 1. This is why it is always less than 1. So usually your lambda you will take less than 1 value, but m is the very, what is m? M is the number of instances, right? You'll get number of instances. So this whole value will become very small. This alpha also will become very small. Then 1 minus you are doing. So each time you are multiplying theta j with theta j, a small number of less than 1. So that's why this reduces the theta j value, right? So the first value is reduces. Intuitively, the first term in the above equation 1 minus alpha by lambda m will always be less than 1. Intuitively, you can see it as reducing the value of theta j by some amount of every update. As you update, because our whole aim is to get theta j value smaller. So it reduces for each update some value less. Again, you are doing minus only. You are not adding anything positive to that. Cost function is always positive, right? Cost will be non-negative. So the first term itself is reducing. Then the second term is also reducing the theta j value. As you progress many iterations, it reduces the theta j values. So this is the regularization of the how we achieve or we address underfitting and overfitting by using regularization. If you do more regularization, it becomes again underfitting. So you should be careful that how much this lambda should be taken. So that is one you should keep in your mind so that you cannot overfit the equation, linear regression or logistic regression, and you get good results provided you take good lambda parameter. Of course, here it is not discussed. There are two types of regularization: L1 regularization, L2 regularization. Hybrid is also there. L1 means, let's say, here we are taking squares. So if you take not squares, mod of lambda of mod theta j, then you are not penalizing too much, because theta j square, as I told you, even if small increase, theta j square will become very high, right? As I told you, 10 to 100 in theta's value, it is only 10 times. But when you take squares, it becomes 100 times, because 10 square is 100, 100 square is 10,000. So that becomes 100 times of the 100. So 10 square, 100 times it becomes more. So when you are using the square terms, you are reducing theta j's very, very small. In that case, some of the thetas which are very, very small, those features which have those small thetas, they won't contribute much. You are already reducing the number of features you can think. So if you take L2 regularization, it is also one way of looking at reducing the number of features, because your squares will become small values for thetas. Those variables which have small thetas, then they don't contribute much. You can actually omit from the equation. That is one way of looking L2 regularization. L2 means power is 2. Another one is called L1 regularization. You want to keep all of them. All of them should be contributed. Then you don't want anything to be penalized too much. Then you will take, instead of theta j square, you will take mod theta j. Means you will only add exactly how much they are weights, not in squares. Then you don't penalize too much, means you won't get it's a small theta value, so that you can eliminate from the equation. That is called L1 regularization. So there are two types of regularization, L1 and L2. The most famous is the L2. That's why the discussion is done on L2 here. But when you go for interviews, you should remember that L1 regularization, we will not use the squares, we'll take the absolute values of thetas, this cost function. That will not eliminate the features. Here, when you are taking more, even theta j square, theta j cube also, if you want to reduce number of features, then you apply theta j cube, then remove those features which have small theta values in the whole thing. Then so that you can reduce features. So L2 regularization is also used for, automatically it reduces the contribution of the many features. So that is the difference between L1 and L2 regularization. So some people will use both terms also, L1 and L2. So when you take up this linear regression, then you will have, we'll see the documentation. We'll see that they'll tell you what regularization you can use. Okay, we exceeded time. We can also discuss this tomorrow, but I'll show you that how you can go and see that documentation. Logistic regression. See here, penalty. Regularization is nothing but penalty, right? If you see here, penalty L2 they took. So you can go and see that what can we give this penalty. L1, L2, elastic, none. These four options you can give in scikit-learn. So default L2 they take, because we have seen L2 they have assigned. Use it to specify the norm used in the penalization. Penalization, regularization is same. The Newton CG, SAG, and LBFGS solvers support only L2 penalties. ElasticNet is only supported by the Saga solver. If none, not supported by the liblinear solver. No regularization is applied. So there are different methods are there. So again, if you take the method Newton CG or SAG, then you cannot take L1. That is what they are saying. If you take other things, you can take these things. So this is how you can see that how L1, L2 can be applied for regularization. So the essential idea is, if you are using L2 means you are also simultaneously reducing the number of features. So again, you can go through the Andrew Nagy videos and whatever they given for regularization. If you haven't understood something, then tomorrow also we can discuss this. I tried my best to give the essence of the regularization after the logistic regression. So again, we will meet. We'll see that if there are any doubts, will be clear tomorrow on logistic regression and regularization of this. Okay, I'll stop it here. We'll meet again tomorrow.